Welcome to this explainer. I gotta tell you, I am absolutely thrilled about today's topic. Our goal here is to completely demystify how we secure modern microservice architectures. We're gonna unpack the inner workings of JSON Web Tokens, navigate the sometimes wild landscape of modern cryptography, and see exactly how all these pieces interlock to create highly secure, infinitely scalable applications. If you've ever wondered how your favorite apps manage to keep millions of users securely logged in without completely crushing their databases, well, you are in the exact right place. Here is our roadmap for today. First, securing the modern microservice. Then, we'll meet the JSON Web Token, figure out how to choose a signing algorithm, throw out a refresh token lifeline, and finally, put the whole shebang together. Let's jump right in. Section 1. Securing the modern microservice, and specifically, the stateless challenge. So let's just dive right into the main architectural hurdle we face with modern apps. I want to throw a fundamental question your way right out of the gate. Think about it. In a classic monolithic app, a user logs in, the server creates a session, sticks it in a database, and hands the user a cookie. Simple, right? But what happens when you have a distributed microservice architecture? Checking a central database for literally every single API request from every single user? No way. That is a massive bottleneck. We desperately need a way to trust a user completely statelessly. To ground this, let's look at a real-world case study from our source material. It's a connected car app called Predictive Car Maintenance. Basically, this app connects vehicles, drivers, and garages. Now, a driver from a specific company just needs to see their vehicle's status, maybe schedule a repair. But a mechanic at the garage? They need deep, granular access to advanced diagnostic data. So we've got to enforce these distinct, highly secure access rules without bogging down the entire system. And this setup brilliantly illustrates how enterprise solutions tackle this exact problem. On one side, you've got an identity and access management system, like Okta, handling the actual user verification and multi-factor authentication. Then on the other side, there's an integration platform like MuleSoft. It acts as an API gateway, routing the traffic and enforcing security policies before any request even touches those core microservices.
Moving on to Section 2, meet the JSON Web Token, essentially our cryptographic VIP pass. Let's peel back the next layer of the onion and see the tech that actually makes this stateless trust a reality.
Enter the JSON Web Token, or JWT. You can really just think of a JWT as this sort of cryptographic VIP pass. Once Okta verifies who you are, boom, it issues this pass. And the true magic here is that it carries all the necessary user info securely within itself. The API gateway doesn't need to phone home to Okta to ask if the pass is valid, because the pass mathematically proves its own validity. How cool is that?
Now, a crucial point here is understanding the stark difference between validation and verification. To actually trust this VIP pass, we absolutely have to do both. Validation just means checking the basic format, right? Like, does it look like a JWT? Has it expired? Verification, on the other hand, well, that's the heavy lifting. That is the mathematical confirmation that the token hasn't been maliciously altered by some bad actor while in transit.
And notice how beautifully simple the structure of a JWT actually is. It's really just 3 base64 encoded parts glued together with little periods. First, you have the header, which tells us exactly how the token is secured. Next is the payload, containing the claims, stuff like the user's ID or their specific role. And finally, the signature. You can think of the signature as this holographic, tamper-proof seal slapped over the whole thing.
All right, Section 3, choosing a signing algorithm and our cryptographic defenses. Because, let's be real, a VIP pass is utterly useless if any random person with a printer can forge it. So let's examine how we mathematically lock these things down.
Let's compare symmetric against asymmetric algorithms. Symmetric algorithms, like HMAC, use one single secret key to both sign and verify the token. It's fast, sure, but it's risky. Asymmetric algorithms, like RSA and ECDSA, solve this risk by using a key pair. You've got a private key to sign the token and a public key that literally anyone can use to verify it. I really want to emphasize a huge point from our sources here. While HMAC is definitely fast and simple, using it to sign tokens is widely considered a massive anti-pattern in distributed microservices. Why? Well, imagine you have 50 different microservices that all need to verify tokens. You'd have to share that one master secret key with all 50 of them. If even a single service gets compromised, your entire system's security completely collapses like a house of cards.
So we go with asymmetric algorithms. Here we're comparing the legacy giant RSA against modern elliptic curve cryptography, or ECDSA. Now, RS-256 is the industry standard. It's highly compatible and incredibly fast to verify. But ES-256, that's the modern marvel. By using elliptic curve mathematics, it achieves the exact same level of security as RSA, but with significantly smaller key sizes. That makes it absolutely ideal for high-throughput mobile and IoT environments.
Now, you might be wondering about the 256 in those names. That refers to the SHA-256 hash function. And this number, 128, represents the actual bits of security you get from a 256-bit hash. It's because of this cryptographic concept called the birthday paradox. Basically, a 256-bit hash gives you exactly 128 bits of security against collision attacks. Long story short, it mathematically prevents attackers from finding two different tokens that somehow produce the exact same signature. It is incredibly secure.
But, the landscape is always evolving, and our source material delivers this ultimate recommendation. If possible, go for ECDSA. Actually, ECDSA is a specific type of elliptic curve cryptography that's faster, more secure, and critically, it's deterministic, meaning it avoids the dangerous random number generator pitfalls that can sometimes cause standard ECDSA implementations to accidentally leak their private keys, and we definitely do not want that. Okay, Section 4, the refresh token lifeline and stopping stolen tokens. So we have an unforgeable token. Great. But we face a brand new vulnerability. What if it simply gets stolen by a bad actor? I want you to use this question to evaluate your own systems. Because JWTs are stateless. And remember, the whole point is we don't want to check the database every single time. They are incredibly hard to revoke once they're out in the wild. If an attacker manages to intercept a valid JWT, they can impersonate that user perfectly until the token expires. There's almost no stopping them. And that is exactly why our core defense mechanism relies on time. Access tokens must be strictly short-lived. By giving an access token a lifespan of, say, just 15 minutes, we drastically minimize the window of opportunity for an attacker. Even if a token is stolen, it becomes completely useless very, very quickly. But obviously, we can't ask our users to log back in every 15 minutes. They'd hate us. So let's walk step by step through the refresh token lifecycle, which acts as our ultimate safety net. When that short-lived access token expires, the client silently sends a separate, long-lived refresh token to the server. The server verifies it, and, this is the crucial part, it rotates it. It revokes the old refresh token and issues a brand new access token along with a brand new refresh token. Now, because refresh tokens have a much longer life and actually hold the power to generate new access tokens, they have to be guarded fiercely. Our sources detail some essential best practices here. Never ever store refresh tokens in local browser storage. Instead, use HTTP-only cookies to prevent malicious scripts from accessing them. Furthermore, the server should only store a cryptographic hash of the refresh token in the database. Treat it exactly like you would treat a user's password. All right, Section 5, putting it all together, the complete security onion. We've looked at all the individual pieces, so now let's assemble the puzzle and see how this builds into a complete, secure architecture. Here is the complete journey of our token. First up, Okta authenticates the user with multi-factor authentication and issues our short-lived JWT plus a secure refresh token. Then, when the user requests data, the MuleSoft API gateway steps in. It intercepts the request, grabs the public key, and instantly verifies the JWT signature. If it's valid, the gateway checks the group claims inside the token to see if the user even belongs to a group that's allowed to access this specific service. That's our coarse-grained authorization. Finally, the request gets passed all the way down to the microservice itself. The microservice looks at the user's specific email claim in the token to decide exactly which pieces of data they're actually allowed to view. And this whole flow elegantly ensures that the principle of least privilege is enforced flawlessly at every single layer. Think of the API gateway as a bouncer checking your VIP pass for the right stamp at the door, and the microservice as the concierge, making sure you only get the keys to your specific room, whether you're a driver checking a schedule or a mechanic diagnosing an engine. We've seen just how powerful and scalable stateless JSON Web Tokens can be for modern microservices. But as we wrap up, I want to leave you with a slightly provocative thought to reflect on regarding your own infrastructure. When your entire security model relies on decentralized, stateless trust built on public and private key pairs, are you fully prepared with a key rotation strategy for the day a master cryptographic key gets compromised? It is a truly fascinating challenge to solve. Thank you so much for joining me on this deep dive and this explainer. Keep building,
keep securing, and I'll catch you next time.